Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. My contributions to physics is not merely a theoretical discovery, nor is it akin to the experimental discovery of the laws of motion of physics. My contributions to physics exist in a separate category, one called extreme scale experiments in computational physics. It has mathematical physics and supercomputers at its foundation. I contributed to physics by experimentally discovering how to massively parallel process across a new internet that's a global network of processors. Theoretical physicists, the likes of Albert Einstein, cannot solve a system of coupled, nonlinear, and time-dependent partial differential equations that in theory can be exactly solved by executing an infinite number of floating point arithmetical operations. That set of infinite calculations is at the calculus core of a general circulation model that's running across a global network of 64 binary thousand commodity processors, or across a global network of as many identical computers. The necessity to execute extreme scale computational physics codes stimulated the development of the modern supercomputer that computes across processors and computes in parallel. That historical milestone in extreme scaled computational physics was crossed at 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the US Independence Day. The milestone was crossed when I experimentally discovered that the slowest 65,536 processors in the world can solve the toughest problems in computational physics and solve them faster than the fastest supercomputer that cost the budget of a small nation. Prior to that experimental discovery, computational physics codes were limited to the resolution of only one processor that is not a member of an ensemble of processors, instead of to the resolution of my ensemble of 65,536 processors. My experimental discovery of massively parallel processing enables extreme scale modelers to derive detailed information from petroleum reservoir simulators and from general circulation models and from the most computation intensive codes in computational fluid dynamics. Conversely, the resolution in computational physics is now limited by the level of parallelism within the modern supercomputer. My technological quest for the fastest parallel processing supercomputer was not an 8-year-long sprint. That scientific quest was a 16-year-long parallel processing marathon across mathematical physics, across physics and supercomputing. I began programming the world's fastest supercomputers on Thursday, June 20, 1974. I began supercomputing in the Computer Center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. On a typical day, I worked for 3 hours from 4 a.m. to 7 a.m. as the janitor at the ceramics building that was a short walk from the Computer Center. The rest of the day, I was more likely to be inside Kidder Hall, the mathematics building at 2000 Southwest Campus Way, Corvallis, Oregon, United States. The mathematics building was a shouting distance from the computer center that housed the supercomputers that I was programming. When I began supercomputing, massively parallel processing, the technological engine that powers the modern supercomputer, was the most beautiful theory in supercomputing. Like any theory, massively parallel processing in the 1980s was an idea that was not positively true. The June 20, 1990 issue of the Wall Street Journal recorded that I, Philip Emeagwali, conducted a never-before-seen supercomputer experiment and did so across 65,536 commodity processors. In that supercomputer experiment, I confirmed massively parallel processing as positively true. In that supercomputer experiment, I upgraded massively parallel processing from a theory to a discovery. To discover is to see something where nothing was seen. The computation-intensive problems that I discovered how to solve in the 1980s and how to solve them across a new internet, that's a global network of processors, were called grand challenges of supercomputing. They were called grand challenges because it was impossible to solve them and, for instance, to execute an extreme scale general circulation model used to foresee otherwise unforeseeable global warming and foresee it across a massively parallel processing supercomputer. They were called grand challenges because no supercomputer scientist knew how to solve the most computation-intensive problems of physics, calculus, and algebra. They were called grand challenges because no supercomputer scientist could solve them with a 64 binary thousand-fold increase in supercomputing speed. They were called grand challenges because the then state-of-the-art technology called vector processing was not contributing much to the speed of supercomputers. They were called grand challenges because parallel processing, that was the hoped-for solution, was considered a huge waste of everybody's time. In the 1970s and 80s, trying to discover a factor of 64 binary thousand increase in computing speed of a massively parallel processing supercomputer that was powered by 64 binary thousand processors was like trying to make the parallel processing machine do the impossible. The mood of the decades of the 1970s and 80s was summed up in an article in the June 14, 1976 issue of the Computer World magazine. The Computer World was the flagship publication of the world of computing. That article in the Computer World magazine was captioned, quote, "Research in parallel processing questioned as waste of time," unquote. 14 years after that article in Computer World, the June 1990 issue of the Siam News, the flagship bi-monthly news journal of record of mathematicians, carried a cover story that described how I, Philip Emeagwali, experimentally discovered how to save time by massively parallel processing extreme scale computations and processing them across 64 binary thousand processors. I experimentally discovered a paradigm shifting speed increase in massively parallel supercomputing that was a factor of 64 binary thousand times faster than what was believed to be possible. I experimentally discovered how to save time by massively parallel processing 64 binary thousand initial boundary value problems of modern mathematics and computational physics. I experimentally discovered how to email and solve those problems and solve them through a new internet that I visualized and theorized and programmed as my global network of 64 binary thousand commodity off-the-shelf processors. My experimental discovery of how to reduce 64 binary thousand days or 180 years of time to solution on only one processor to only 1 day of supercomputing across 64 binary thousand processors was copied by Chinese supercomputer manufacturers. Chinese supercomputer scientists use my experimental discovery of massively parallel processing to solve initial boundary value problems arising in extreme scale computational physics that would have taken 30,000 years to solve on only one processor. Chinese supercomputer scientists can now solve the same mathematical problem in 1 day and solve them across a network of 10,649,600 commodity off-the-shelf processors. On the 4th of July of 1989, massively parallel processing supercomputing conflicted with the established truth, namely vector processing supercomputing. I was personally and professionally attacked by supercomputer scientists that opposed the radical idea of simultaneously solving 65,536 problems at once or in parallel and across 65,536 processors instead of solving only one problem at a time or in sequence on only one processor that is not a member of an ensemble of processors. For those reasons, my experimental discovery was dismissed as a mistake and was rejected by the supercomputer community. The experimental evidence that the massively parallel processing supercomputer works was slow to come at first, but eventually my experimental discovery that occurred on the 4th of July of 1989 convinced the naysayers that parallel processing works. The experimental discovery of the massively parallel processing supercomputer, mocked and contested as it was a paradigm-shifting moment in our understanding of what makes computers faster and makes supercomputers fastest. The paradigm shift was from computing and communicating in the singular sense to computing and communicating in the plural senses, and to computing and communicating across a new internet that was defined and outlined by a plurality of commodity off-the-shelf processors and email wires. Parallel processing, once the stone that was rejected as rough and unsightly, is now at the foundation of modern computer science.
Insightful and brilliant lecture.